Thank you, Hendrik, for the introduction. You know that the monitoring of breath is an important tool, not only for the analysis of upper airway diseases, but also for the lower airway diseases. And we understood how important it is during the pandemic period. But it's also interesting for application to sports to improve the performance of athletes. Now the breath behavior is complex because it's not symmetrical because the two nostrils, and not only for pathological condition that could be related to colds, also to deviation of nasal septum, but also to natural alternation of congestion and decongestion of nostrils. So we need a bilateral monitoring. This is the golden standard. The golden standard is this spirometry, let's say airflow monitoring by pressure sensor. And you can see by yourself, it's not so comfortable for users because you need to put wires, cannulas inside the nostrils. It is supervised and definitely is not for babies. We follow a different approach based on the temperature measurement. The rationale is that when we perform inhalation and exhalation, we are changing the local temperature close to the nostrils, because when we put air inside, outside, we have a gradient of temperature. So the gradient, the pattern of temperature resembles the breath pattern. So we can derive breathing pattern starting from the temperature. And here where the flexible electronics is useful, because when combined with the radio frequency identification, we could have the simplest devices possible to attach close to the nose with the minimum number of components to detect the temperature. We don't need battery because all the energy will be provided by remote by a reader. Then this is our device, very simple. Is asymmetric T-match dipole like this, that is sandwiched between elastomers to make it soft. And in particular, we use two different kinds of elastomers. Ecoflex in between the antenna is between Ecoflex, and then Sylbion, which is very sticky for application on the skin. Ecoflex is less sticky, so it's more suitable to all the antenna. Here there is the sensor that's capable to perform a measurement of temperature with the resolution and accuracy, which are, we can say, suitable for monitoring the small gradient that we have close to the nose. Then we have to pack two of these, okay, so that the sensor will be put very close to the nostrils and can collect nearly independently the airflow temperature. The device is fabricated, as was shown before in the other presentation, by producing a 3D printed resin mold. Then we put the materials, both Sylbion and Ecoflex are big components materials, so we have to mix and the gassing, pouring, and then you put in a oven for a few minutes in order to make it more consistent. The device is overall soft, can be attached gently on the skin. You can remove, wash, and reuse many times. So it's single use for the patient, but a user can use it many times. Here the experimentation, the electromagnetic analysis in terms of realized gain. We have a phantom that we've used for the design. I didn't spend so much time for the design. Anyway, you can appreciate that the left and the right sensor provide the same response. So the system is quite stable and symmetric with respect to the interrogation. Also, you can appreciate a very flat response here. This is due to the use of here an auto-tuning device that modifies internal impedance in order to compensate possible mismatching between the antenna and the microchip when we move from a user to another one. This is an important topic, is the cross-sensitivity. It means each sensor should measure only what is coming outside a nostril. So we close a nostril and then measure both and vice versa. And you can see that Here, for instance, the flat one is for the closed nostril, and the other one for the free nostril. So we can say that the two sensors are reasonably independent. The cross sensitivity is 0.1 degree, which is less than the sensor precision. So we will not really recognize it in a practical application. The experimentation with, in comparison with the golden standard, let's say a pneumotachograph that include cannulas inside the nostrils, our sensor in the positions, and then we collect the differential pressure data by a transducer and an oscilloscope to visualize. And on the right, we have the RFID system that collect temperature in a remote way. We evaluated with some volunteers, we emulated different kinds of breathing, quiet, apnea, deep, tachypnea, bradyapnea, that's by a metronome inducing different rhythm of respiration and deep. You can say this is the cannulas and the wireless sensor. They are quite comparable. The correlation is very high, it's close to 0.8. And also you can see the small difference between the left and right nostrils, which is the same that we have in the two different methodologies. This is because in the real life, effectively, you don't have a symmetric respiration. Now, we also had some statistics with 10 volunteers, and we extracted some features like the respiratory rate, the peak ratio, let's say the ratio between upper and lower peak, and then the peak between the left and right channels. This is the difference with respect to nasal cannula measurement. And here we have the cumulative distribution function. The more vertical and the more on the left, the best the agreement is among the two methods. And you can see the agreement is very good. And in particular, the difference in the evaluation of the frequency is very, very negligible. So it's a really accurate methodology capable to do the same of the golden standard. What we are not able to do here currently is to measure the volume, because the volume is related to the flow of air. Instead, we are measuring the temperature. So probably we need a calibration. Now, to be honest, it's not so, it's a little bit impacting, no? I have a little bit bird I cannot wear over me. It's not easy to eat, to speech. So what we did is to redesign the device, making much smaller, just the two loops like this. And then the two loops can be folded and be inserted into septum like a small ring. We designed two versions for adult and also for babies, which is a little bit smaller. And this is fabrication by using polyamide, flexible polyamide, engraved by a laser cutter. And then we put inside the PDMS in this case, because it was too small to use elastomers, sticky elastomers. And this is the final object. And as you can see, not so different than a standard ring that some female and also male use. Okay, so this is the application of a volunteer and a phantom of a baby. Okay, as I told you, not so different. And performance are very good, even better than the other one, which is larger. We can see here that left and right are really, really symmetric. And we have also a broad range of interrogation. So we don't need to stay exactly in the front of the antenna. We can tolerate also some misalignment. And the maximum distance in the best case is up to 8 centimeters, more or less 60 in the average. So to wrap up, I concluded to wrap up, we have demonstrated that the clinical meaningfulness of temperature-based respiratory pattern and the system based on epidermal sensor attached below the nostril. With the mustache-like device, we had a very low cross sensitivity and overall more than 40 centimeter distance. So it's comfortable for a fixed reading. Then the improvement with the septum ring device, the read distance it was even more, and is inherent zero cross sensitivity because the two sensors are isolated, naturally isolated by the nose, by the tissues. And then we are able to collect here a much deeper dynamics of the temperature. So the smaller one are the mustache-like, instead the longer one are the septum. So with the septum, we will have up to 4 degrees of variation gradient, so that we have a very high signal-to-noise ratio, so high capability to detect the features. Just to show you a possible example in real life, these are a spectrogram measured by the systems. So here we have the respiratory rate in Earth, and here the time. Okay, so we change the respiration in this way by inducing with a metronome, and you clearly see the variation of the frequency. In this other case, there is an activity, a cyclet here. You will see that the change of the respiration rate as the exercise goes on. That's all. Thank you for the attention.